Hi, everybody, and welcome to this session of the Spectral Geometry in the Clouds seminar. So today we have the pleasure of having Luigi Provenzano from La Sapienza in Roma, who will talk to us about isoperimetric and geometric inequalities for the magnetic Laplacian. As usual, if you have any questions during the talk, don't hesitate to unmute yourself or write the question in the chat and we'll relay it to Luigi. So Luigi, the floor is yours.
Okay, thank you very much, Jean, to you, to Laura, and to Alexandre for the kind invitation. As always, very happy to give a seminar here. And today I will speak about some inequalities of geometric type and also isoperimetric for the magnetic Laplacian. And I will talk of results obtained in two joint works with Bruno Colbois from Neuchâtel, Corentin from Padova, and Alessandro Savo, who is a colleague from Rome. Let me start. I will just start very slowly by defining what kind of operators and spectral problem we are considering, and so by introducing the magnetic Laplacian. So I will be in R2 on the plane, and I will consider a real one-form A. I write it f dx plus g dy, f and g are smooth function, and I will call it a potential one-form. And then the two form given by the exterior derivative of A is what I will call a magnetic field. So in this case, I can identify it, if you wish, with a function. Okay, now, given a smooth complex valued function on the plane, I define its magnetic differential. This is just a perturbation of the usual differential. As you can see, it's just the usual differential du minus iua. I is the imaginary unit, and A is the potential one-form. So it is a perturbation of the usual differential of a function by a complex one-form. A is real, and I have I, the imaginary unit. And then I have the adjoint of this operator, formal adjoint, is the magnetic codifferential. I've written an explicit form of this operator. And then using the magnetic differential and codifferential, as you usually do with the differential and the codifferential, I define a magnetic Laplacian. It is just delta A, magnetic codifferential of the A of U. If A is 0, you see you have just the usual Laplacian on functions. It has an explicit form. I've written it here, but really we will never use during the talk. So maybe I could also not write it to not make confusions. Anyway, so this is the magnetic Laplacian. You see, it is the perturbation, let's say, of the usual Laplacian by a complex potential. And I right away want to present you one of the most important features of this operator I will use widely in this talk, which is the gauge invariance. Namely, if you have the magnetic Laplacian given by a potential one-form A, and the potential one-form A plus d phi, namely perturbed by an exact one-form, well, these two operators are related by a unitary operator. This relation holds. So these are unitary equivalent. When we will speak about self-adjoint realization of this operator and spectra, we will see that the corresponding spectra will be the same. I will get to that in a few moments. So this relation is what I call gauge invariance. We can ask even less than perturbing a one-form by an exact one-form, but this is not, I don't want to speak about that. Let's just take this formula as it is. And note that if I take the exterior derivative of A plus d phi, it doesn't change. It is the exterior derivative of A, because perturbing a potential one-form by an exact one-form does not change the magnetic field. So this magnetic field is not touched by the change of gauge. Just another way of representing, let's say, generating this magnetic field. Okay, now, what is the eigenvalue problem I'm going to consider? I consider an bounded and smooth domain of the plane, and I consider the Neumann eigenvalue problem for the magnetic Laplacian. The eigenvalue equation is the same as the Laplacian, a magnetic Laplacian of U equal lambda U in omega, and then we have magnetic Neumann boundary condition. Namely, if you wish, the magnetic gradient of U times the outer unit normal is equal to 0. If A is 0, this is the usual Neumann boundary condition. Nu is the outer unit normal. Of course, as usual, this problem is understood in the weak sense, namely in the sense of quadratic forms. And again, nothing is really different from the Laplacian case. The quadratic form is given by the L2 product of the magnetic gradients, magnetic differential if you wish, instead of the usual gradients. And the weak formulation is studied in the magnetic Sobolev space, which is the correct energy space for this problem. It is the set of functions in L2 with magnetic gradient, magnetic differential in L2. If A is smooth, this is nothing else than the usual Sobolev space H1, of course. In this talk, I will consider, in fact, smooth potential one form A, so the Sobolev space H1A is just H1. Okay, so this is nothing new for all of you, I imagine. Okay, and again, nothing really new. If A is smooth, then it is easy to see that we have an increasing sequence of eigenvalues of finite multiplicity. They are non-negative and divergent to plus infinity. And in particular, the first eigenvalue is given by the minimum of the Rayleigh quotient. And the Rayleigh quotient looks like exactly the same as the Laplacian, but we have the L2 norm square of the magnetic differential. That is what I call the magnetic energy, dAu square, integral over omega. And this is non-negative. Now, when A equal to 0, we have the eigenvalues of the Neumann Laplacian. But if you remember what I was telling you before about the gauge invariance, this is also the case when A is an exact one form. So namely, the eigenvalues of the magnetic Laplacian with an exact one form are just the eigenvalues of the usual Laplacian, and the eigenfunction are just the same multiplied by a phase. Nothing more. And in this case, in the Neumann case, the first eigenvalue is 0. So I will label lambda 1 0 in the Neumann case, and the first positive one is the second one. And in general, by gauge invariance, we have that if we perturb a potential one form by an exact one form, the Neumann spectrum does not change. It is the same. Okay. I have this bar here that I want to. Okay. Where is okay? And today I will consider a specific magnetic potential. It is this one, beta over 2, where beta is a positive constant, times minus y, the x plus x the y. X, y are the usual Cartesian coordinates in the plane. So it looks like a very harmless potential, but it is not really that harmless. And so this gives rise to a constant magnetic field of intensity beta. In fact, the exterior derivative is just beta times the volume form. So it's a constant magnetic field. So I will consider today the constant magnetic field case. As soon as beta is not 0, is positive, the spectrum does not coincide with that of the Laplacian. And in particular, the first eigenvalue, really the minimum of the Rayleigh quotient, is strictly positive. You can prove it in various ways. It is a classical argument by Shigegawa and also by Faber. And yes, as soon as beta is non-zero, the first eigenvalue is positive. And I will be interested in this talk in the ground state energy in lambda 1, especially in lambda 1. Okay, I can go on. This is more or less the setting and what kind of eigenvalues I'm going to consider. Now, before going really to the results, to the geometric bounds and the isoperimetric inequalities, what I want to do really is to give you a list of properties and a list of maybe even easy examples to convince you that some features of this problem are quite tricky and that this potential is not really harmless as it may seem. So the first property, which seems really trivial to state, is that the spectrum is invariant under isometries. Of course, it's natural, the field is constant, but in general, for a magnetic Laplacian, this is not the case. For other potential like Karnoff-Bohm, and for general potential, this is not true at all. But in this case, it is invariant under isometries, and the proof deeply relies on the gauge invariance. You have to change gauge in a suitable way to prove the invariance under isometries. Now, what happens when the domain undergoes a homotopy of factor alpha? So if you take eigenvalues of alpha omega with the magnetic field beta, well, the eigenvalue become 1 over alpha square. This factor remains the one of the Laplacian of the eigenvalue of omega, but you have to modify also the intensity of the magnetic field, which becomes beta alpha square. Okay, this is just an easy computation. And what happens for small beta? So now you fix the domain omega and take beta to 0. Take a small beta. Well, as beta goes to 0, you imagine it is easy to prove that you converge towards the Neumann problem. This is a regular perturbation of the Neumann problem for beta small. And the first eigenvalue behaves like a constant, which can be computed explicitly, C of omega times beta squared. So it goes to 0 quadratically in beta. This constant is related to the torsional rigidity of omega, but I will not be interested in this now. And if you combine these two behaviors, you get that if you fix now beta, the intensity of the magnetic field, and you shrink homothetically omega to a point, you take alpha omega and send alpha to 0, well, the first eigenvalue behaves like a constant alpha square beta square as alpha goes to 0. Namely, if you shrink homothetically a domain to 0, the first eigenvalue go to 0. But in general, is not true, as this example would suggest that if you have a domain whose area is small, then the first eigenvalue is small. This is not true at all. And this simple example shows this. So you consider a simple closed curve gamma, namely it bounds a simply connected domain, and consider the tube of width h around this curve. Well, you can consider the magnetic spectrum on this tube, on this small tube, and you consider the limit of the eigenvalues, in particular of the first one when the width goes to 0, and you can explicitly compute the limit spectrum. In particular, the first eigenvalue is quite explicit. It's 4 over pi square, the length square of the curve, times the minimum of these quantities, the minimum over the integers of n minus beta, the area over 2 pi squared. This number beta times the area over 2 pi is not a casual number. It is the flux of the potential around the curve gamma. So when this flux is integer, this minimum is 0. Otherwise, it is not 0. So you have a domain whose area is going to 0. And if the flux is not integer, the first eigenvalue stays uniformly bounded away from 0. So small area does not imply small eigenvalue, for example. I will consider again this example later when I will speak about the isoperimetric inequality. Think of the homotopy before. If you instead have a small disk of a small area, there the eigenvalue goes to 0 because you are shrinking it homothetically to 0. But not in this case of the tube around this curve. Okay. Now, what happens for large beta? Also here, you have strange behavior of the first strange. Not really strange for people working in this area, but with respect to the Laplacian, it's quite strange. So, as beta goes to plus infinity, and you have your domain fixed, the first eigenvalue is going to plus infinity. And in the first order is going like theta 0 beta, where theta 0 is a universal constant called the Jean constant, 0.59, etc. And again, if you combine these with homotheties, now you take fixed the magnetic field beta and take an homotety of the domain and send alpha, the homotety factor, to plus infinity. And then the eigenvalues goes always to theta 0 beta. So the limit is independent on the domain. If you take a domain, magnetic field fixed, take an homotety, and alpha goes to infinity, the limit is always theta 0 beta, which is, again, a strange behavior. You can have very large volume, but the eigenvalue goes to this number. Let me say some other simple examples. If you are able up to isometries to place your domain in a strip with epsilon small, and this regardless of the area of the domain, of its simply connectedness or whatever, if you are able to place your domain inside a strip, as most thin strip, then the first eigenvalue is less or equal than epsilon square beta square over 4. And this does not really depend on the shape or the area or whatever of the domain. Okay. And moreover, you can produce a lot of other examples. Here I've written just a few words. For example, domains with in radius uniformly bounded below away from zero, but still very small first eigenvalue. So you can produce very different situations. So to say that it's not really an easy task to guess which geometric properties enter the bounds, let's say, reasonable bounds for this eigenvalue. What kind of geometric quantities really affect and in which way the eigenvalues of this operator. So that's why I'm saying that it's a bit tricky. And what about isoperimetric inequalities? Well, let me recall that in the Dirichlet case, you can consider this problem for the magnetic Laplacian with Dirichlet boundary condition. Well, you have a Faber-Krahn inequality, and it has been proved by Erdős in 96. Namely, among all bounded domains of fixed area, the disk is the unique minimizer. So this is proved, and this holds for any planar domain. Okay, it's again not a simple proof. But on the other hand, for the Neumann problem that we are considering, the reverse Faber-Krahn inequality does not hold. What I mean by reverse Faber-Krahn inequality, I mean that among all bounded domains of given area, the disk is the unique maximizer. I call it reverse Faber-Krahn because it refers to the first eigenvalue, to the true first eigenvalue, the minimum of Rayleigh quotient, we call it. And the reverse because the inequality goes in the opposite direction. And this does not hold for the Neumann problem, at least if omega is not simply connected. And you may now think of the example of before. Think of the very thin tube. Take this thin tube when the area goes to zero and when the eigenvalue does not go to zero. And take the disk with the same area. When the area of the disk go to zero, the eigenvalue of the disk go to zero. And so you really simply can check that for non-simply connected domain, this inequality cannot hold. Previous examples, of course, were given by Elfer and Fournet in their books. And in fact, they conjectured that this inequality should hold for simply connected domain. And this is what I will call in the last part of the talk. I'm sorry, but I want to insist in a couple of slides more with examples. Because I want to convince you that in particular, this Neumann problem is tricky. And here I've plotted a picture which represents the behavior of the first eigenvalue on a disk of radius r. So here the variable is r, so it's the radius of the disk. Here I fixed the intensity of the magnetic field to be 1. So the red branch is representing the first Dirichlet eigenvalue of the magnetic Laplacian. You see, it behaves quite like the first eigenvalue of the Laplacian. When the radius is 0, it goes to plus infinity, and then it smoothly decreases, and it goes to 1 beta in general, which is the intensity of the magnetic field. And it is the red branch. For the Neumann case, the first Neumann eigenvalue, when the radius is 0, is 0. We have seen it goes to 0. And then it starts increasing. It goes quadratically to 0. It starts increasing. But then it starts having this weird oscillating behavior with these angles. And then its limit is not 1, but it is theta 0. In general, it is theta 0 beta, as we have seen, in fact. It is the behavior under homotheties. So you have this strange oscillating behavior. Why this strange oscillating behavior? Because as it's customary, when you look for the eigenvalues on the disk, you separate variables. So the first eigenvalue will be given by the minimum of the first eigenvalue of a family of Sturm-Liouville problems, so a minimum over some branches of eigenvalues. And in this case, these branches keep intersecting, and this gives rise to this oscillating behavior. I will be back on this picture later, so I will not stay to this picture for now. I will explain it better later. So just to explain these weird oscillations with the angles, it's just intersection of eigenvalue branches. Okay, and now I will pass to the, let's say, first part of results, where I will give a summary of results on bounds for the eigenvalues, in particular bounds for the first eigenvalue. And in particular, I will start with a simple, stupid thing that one will do always when looking for upper bounds. Well, for the min-max principle, we have that the first eigenvalue is always less or equal than the Rayleigh quotient of any function in H1 that you can plug inside one. put some function, hope to be lucky, and get an upper bound. And in the case, in the Neumann case, the first, let's say, stupid or ingenious try is to take u=1, the constant function. But what we get is this ugly upper bound where you have a beta square, which is good for beta small, but not good for beta large, because for beta large, the behavior is linear in beta. And then you have this integral of x squared plus y squared, which seems to depend on the position, but the eigenvalues are not are invariant under isometry. So really trying to get good test function is not easy, and you have to really play with gauge invariance, as I will mention in a while. So let me start by stating yes.
Luigi, I have a quick question. So on the previous slide,
yes,
does it make sense as a bound to make this translation invariant by taking, say, the inf over positions or something like that?
Yes, you can do it, but still is not a good bound, because you see the other reason is that it depends quadratically in beta. And this may be good when beta is small, because you know that the eigenvalue goes quadratically with beta when beta is small, but goes linearly in beta when beta is large. So you see, you can do what you say, but you still not get a good bound in the sense that we were looking for. Okay.
Okay. Thanks.
Okay. And so let me state the first results on upper bounds for lambda 1. The first bound that we get that was quite surprising for us is that a universal upper bound for any bounded domain in R2, simply connected or not, is beta, and it is strict. All eigenvalues, the first eigenvalue of any domain is strictly less than beta, always strictly less than beta. And if omega is simply connected, we have a more precise bound. It is beta times 1 minus e to the power minus the flux, beta times the area over 2 pi. And here you really see that in the simply connected case, small area implies small eigenvalue. This is true for simply connected domains. This is not true, as we have seen, for non-simply connected domains. And here the point is that the proof, I will not speak about proof in this part, but to say just a few words, it relies on an averaging procedure. We really average over a family of eigenfunctions, of global eigenfunctions corresponding to what is called the first Landau level. So this operator on the whole plane has a discrete spectrum, but each number in the spectrum has an uncountable family of generalized eigenfunctions, let's say, the Landau levels. And we average and we consider as test function a suitable average of these global eigenfunctions, let's say. I don't want to enter into these details. While the second one, the bound for simply connected domains, uses gauge invariance and the suitable test function. I will state a second upper bound. In the next slide, I have pictures which explain better the result. For certain families of domains, we have improved the upper bound to theta 0 beta. In particular, if the domain is a subgraph, if the domain is self-tiling, and if the domain satisfies some strange condition that it's better that I show you in the picture, then the first eigenvalue is upper bounded by theta 0 beta. And in some cases, these inequalities are strict. So we have even a better bound, which really does not depend in some sense on the geometry of the domain. And these are the kind of domains for which this bound holds: subgraph 1, self-tiling domain trees, and domains that are in a half strip and that contain a small rectangle, and after that they can do whatever they want. Anyway, these were examples where we were able to prove this upper bound, even if we think that theta 0 beta may be a strict upper bound for any domain, but really it seemed so simple inequality, but very hard to. We tried very, very hard for a long time. Not one thing, disks of radius r do not fall in these categories. So it is an open question to prove that the first eigenvalue of disks is less than theta 0 beta. And I have to mention a recent paper by Corentin and Bernard L, where they do a deep study of the eigenvalues, of the Neumann eigenvalues of the disk with magnetic field beta, and they study also this conjecture. That picture that seems quite clear when you plot with Mathematica is really hard to study analytically in detail. So it's very hard. Okay, I will do a fast resume of other bounds before passing to the isoperimetric inequality. In fact, we have considered bounds for higher eigenvalues, in particular for averages of eigenvalues. And again, the interesting thing in these bounds is that, again, this flux enters. In particular, we prove that the average of the first k eigenvalues, the whole average, is less or equal than beta when k is less or equal than the flux. Again, this flux, beta times the area over 2 pi. While for larger k, we have the upper bound given as usual by 2 pi k over omega, which is the by limit of this average, plus a remainder term, which goes to 0 like 1 over k and oscillates. It presents still this oscillating behavior and goes to 0. And these imply bounds for the single eigenvalues and for the trace of eternal. And then, but this is a completely different chapter. Maybe, I don't remember if Bruno talked about the lower bounds in the past year. I don't remember well, but we prove lower bounds, which are more trickier in some sense, which depends on beta, on the intensity of the magnetic field, and on the rolling radius of the domain. And the dependence is quite good because it reflects the quadratic behavior in beta when beta is small and the linear behavior in beta when beta is large. So they are quite reasonable lower bounds. And finally, let me mention that we performed also an analysis on simply connected Riemannian surfaces and also a variable magnetic field. So you take a smooth one for A, which gives rise to a variable magnetic field beta. And again, on these simply connected surfaces, a universal upper bound is given by the L infinity norm of the magnetic field. Even if maybe it's not this the true best bound, but it's, you see, still a quite neat inequality. Okay, and this was a bit of a summary of kind of bounds that we proved in a first paper with collaborators. And then we addressed the problem of the reverse Faber-Krahn inequality, the isoperimetric inequality for the first eigenvalue. Okay, and this will be the last part of my talk. Well, in their book and papers, Elfer and Fournay conjectured that for any simply connected domain and any intensity of the magnetic field, you should have the reverse Faber-Krahn inequality, namely among all bounded domains of fixed area, the disk is the unique maximizer. And we recall that, again, this is not true if omega is not simply connected. I will state now the result, but first, in order to state the result properly, I want to go back to the eigenvalues of the disk to show you again that picture and you explain just a couple of things that are needed to understand the result. And so this picture seems quite different from the other one, but it's essentially the same. Here I've plotted the first eigenvalue now as a function of beta, of the intensity of the magnetic field for the disk of radius 1. Here the disk has radius 1, and I plotted the eigenvalues as a functions of beta. Now you have a disk of radius 1. You want to compute the eigenfunction and eigenvalues of this magnetic Laplacian. What you do, as usual, you look for eigenfunction in this form, a radial part, V of r, times an angular part, e to the power in theta, where theta is the angular variable and n is an integer number. Okay, and so plugging these ansatz inside the equation, you see that the radial part must be an eigenfunction of some Sturm-Liouville problem that depends on n, on the integer number n. So you take the first eigenvalue of any of these Sturm-Liouville problems, and you take the minimum, and this will be the first eigenvalue. So here I have plotted the branches of these Sturm-Liouville eigenvalues depending on beta, and the minimum, you take the minimum of all these branches gives you the first eigenvalue. Okay, this is just standard, separation of variables in the case of the disk. And I've written here what Sturm-Liouville problem you get is just this one, but it's not really important. Okay, it's not really important. This again is what I've just said to you before. The first eigenvalue of the disk of radius r is the minimum among all integers n of the first eigenvalue of the Sturm-Liouville problem indexed by n. And what you can do is you can note that the existent number, a beta star, is 3.84. I will show again in the previous picture, such that the first eigenvalue of the disk, radius 1, is given by the radial eigenvalue. That is the eigenvalue corresponding to the Sturm-Liouville problem with n equal to 0. Let me go to this picture again. You see, when beta is to 0, is equal to 0, and when it's still it is smaller than beta star 3.8, the first eigenvalue is given by the red branch. The red branch is the branch of the first radial eigenvalue. So in this region, the first eigenfunction is real and radial, and the first eigenvalue is given by the corresponding Sturm-Liouville problem. Now you can rephrase this for a disk of any radius, and essentially what you get is that if beta times the area of the disk is less or equal than this beta star pi, then the first eigenvalue of the disk of radius r is real and radial, is given by the radial eigenvalue, okay, by the red branch. So that was a small summary of the analysis on the disk that I need to state finally the result. And the result is this. Let omega be a simply connected domain of the plane such that beta times the area is less or equal than beta star pi, where beta star is this 3.8, etc. And then we have the reverse Faber-Krahn inequality. Lambda 1 of omega beta is less or equal than lambda 1 omega star beta, where omega star is the disk with the same area. And we have the equality case. Equality, of course, if and only if omega is this disk. Let me rephrase again this to be more clear. You can rephrase this theorem as follows. Let omega be a simply connected domain such that the disk with the same area has a real and radial first eigenfunction. And then you have the reverse Faber-Krahn inequality, and plus the equality case. So we have proved the reverse Faber-Krahn inequality in this first region, the region where the eigenvalues of the disk, the first eigenvalue of the disk is real and radial. So this is the result up to now. And let me, okay, yes, I have some time, 10 minutes. I have 10 minutes more or less. And I will speak just a bit about the proof, just some ideas. I will not enter at all into the details. And the proof relies in the classical methods of prescribed level lines of Rayleigh and Ritz, but combined with this gauge invariance. Let me explain what I mean. Now, if we take a simply connected domain, any one form A with exterior derivative beta give rise to the same spectrum by gauge invariance because it differs from the standard potential, the one I stated at the beginning, by an exact one form. And then the spectrum is the same. Namely, on a simply connected domain, I can consider the magnetic Laplacian with any one form A with the same exterior derivative beta with constant magnetic field, because these are all gauge equivalent. And so I have to choose a right gauge for this problem, tailored on the domain omega. And this right gauge is the so-called Coulomb gauge. What potential one form I take? I take minus beta times star deep C. I will explain what is star deep C. Star is the Hodge star operator, and C is the torsion function. Is the solution of the torsion problem on omega. What is this star deep C? You can think, for example, of gradients. You take the torsion function, you take the gradient of the torsion function, it is a vector field, and you rotate it by 90-degree counterclockwise. And this is, looking as it is in form, star deep C. The gradient rotated by pi2 counterclockwise, and then multiplied by minus beta. This is just that. And you can check that the exterior derivative of this potential one form is exactly beta times the volume form, meaning that the magnetic Laplacian with this potential is gauge equivalent with the one given by the standard potential that I defined in the beginning, beta over 2 minus x dy plus y dx. And for a domain omega, I will use this potential one form to study the magnetic Laplacian. Okay, get back to the min-max principle. I have that the first eigenvalue is, of course, the minimum of the Rayleigh quotient with this new potential, A omega. And now I want to use test functions which are constant on the level set of the torsion function. I'm using all the possible real valued test functions that are constant on the level set of the torsion function. That is, these are functions that depend only on the value of the torsion on its level set. And these are functions actually of one real variable. The point is that it's not the value of the torsion on its level lines the correct parameter variable to study this problem, but it is the area of the super level sets. So we, instead of using T as a parameter, we use A. A is the area of the super level sets of the torsion function. And so a function which is constant on the level lines of the torsion function is actually a function of the area of the super level set. You can take a look at the picture below. At the point X, the function that we are using in the min-max are functions that depend only on the area in orange of the super level set. So that's the change of variable that we will perform to study our problem. And these functions on one variable are defined on the interval 0, the total area of omega. So when we'll study this problem on domains with the same area, after a change of variables, we will end up on the same interval, 0 area of omega. So get back to the min-max principle. The first eigenvalue, of course, now is less or equal than the minimum of the Rayleigh quotient over all these functions constant on the level set of the torsion function. So we are testing with real valued functions. So the norm square of the magnetic differential is just the norm square of the differential of u plus u squared times the norm square of the potential. But the potential is the gradient rotated by 90 degrees. So the norm of the potential is just the norm of the gradient of psi multiplied by beta. So at the end, we want only the torsion function psi to enter into this Rayleigh quotient. So we change variable, we use the Guaria formula, and finally, the Rayleigh quotient is transformed with this test function in a Rayleigh quotient of function of one real variable A, which is the area of the super levels. And so you see that the first eigenvalue of the magnetic Laplacian is less or equal than the minimum of this Rayleigh quotient of function of one variable over a suitable subspace of L2 of 0 omega. Meaning that the first eigenvalue of the magnetic Laplacian is less or equal than the first eigenvalue of some Sturm-Liouville problem, which is associated with this quadratic form. But where is all the geometry of the domain? Well, it is in a weight that appears in this Rayleigh quotient of functions of one variable, this g of omega. What is this g of omega? It is a measurable function, and it is minus the derivative of the distribution function, the area of the super level set. So all the geometry is inside this weight. The geometry of the domain is translated in this weight of a Sturm-Liouville problem. And what we get is that this function is in L1 and is always greater or equal than 4 pi. And this weight is identically equal to the constant 4 pi if and only if the original domain was a disk. So all these weights are measurable function greater or equal than the constant function 4 pi. And these weights are 4 pi only when omega is the disk. Okay, so let's put together all these facts. The first magnetic eigenvalue is less or equal than the first eigenvalue of a Sturm-Liouville problem associated with this Rayleigh quotient. I have just restated it in this way. It is a standard Sturm-Liouville problem where P and Q, the weights, the Sturm-Liouville equation, depend on the geometry of the domain, on the derivative of the distribution function. This is the first fact. We upper bounded the magnetic eigenvalue with the eigenvalue of a Sturm-Liouville problem with a weight. Second fact, and what happens if we do all this procedure with the disk with the same area, starting from the disk omega star? Well, one could say some magic happens, but actually not, because it is totally natural. The Sturm-Liouville problem that you end up with when you put g of omega star that is identically for pi, this is the weight for the disk, is exactly the Sturm-Liouville problem solved by the radial eigenvalue. So when you do the same computation of the last slide for the disk, the Sturm-Liouville problem that you get is the one of this red branch of the real and radial eigenvalue. And we recall that the radial eigenvalue is exactly the first eigenvalue of the disk as long as beta times the area is less or equal than beta star pi. So to conclude, we just need to prove a monotonicity for the first eigenvalue of these Sturm-Liouville problems, namely to prove that the first eigenvalue of this Sturm-Liouville problem with a weight g greater or equal than 4 pi is always less or equal than the first eigenvalue when the weight is the constant 4 pi with the equality case. Now, this claim it is easier to prove if this weight is smooth enough. If the domain is convex, this is a quite nice and smooth function, and you can do computation quite easily. In this case, we prove that if you have two weights greater or equal than 4 pi, and the weight G1 is greater or equal than G2, and they are not equal on a full measure set, then you have the reverse inequality for the eigenvalues of Sturm-Liouville problem. Eta 1 of G1 is strictly less than eta 1 of G2. And this is done computing a derivative of the eigenvalue of the Sturm-Liouville problem obtained by a convex combination of the two weights. So Feynman-Hellman formula, and study the sign of the derivative, and we prove that it has sign, negative sign. And this concludes essentially the proof in a smooth case. I have really hidden all the technicalities that are essential in this part here. And in general, this weight is only piecewise smooth, and it has just a finite number of singularities. But what you do is you approximate the corresponding Sturm-Liouville problems with regular ones and pass to the limit, gain some technicalities, but you can manage that. And this concludes the proof. So last slide, final remarks, just to again stress the fact why it is important, this simply connectedness. We have seen that if omega is not simply connected, the inequality is not true, in fact. But if you want to consider on any domain, also non-simply connected, the potential one form minus beta star the psi, so start with this potential one form instead of the standard potential, the one defined globally, then the reverse Faber-Krahn inequality holds. The point is that in the non-simply connected case, two potential giving rise to the same field are not necessarily gauge equivalent. So this proof, of course, does not give the false result that the reverse Faber-Krahn holds for any domain. And again, let me stress what we really have proved. We have proved that in the simply connected case, the first eigenvalue of the domain omega is less or equal than the first radial eigenvalue of omega star, namely of the disk with the same area. And this first radial eigenvalue is actually the first eigenvalue in that region when beta area of omega is less or equal than beta star pi. So in order to complete the picture, one would would like to prove the same inequality, replacing this red eigenvalue by all the other branches. But it's not really easy. So that's the end of my talk, and I thank you for your attention. Okay, thank you very much. And these are the references.
Thanks a lot, Luigi, for this talk. We have time for questions now. You were saying that in the non-simply connected case, the inequality is simply not true because of this lack of gauge invariance.
Yes. So the inequality seems to be natural if you consider this A omega for any domain. The point is that that gives rise to the constant magnetic field. The point is that the eigenvalues given by this potential one form in the non-simply connected case are not the same of the standard potential, which is the natural one studied by the physicists, which is of course globally defined, is the relevant one. So this method, which I think catches the point behind the reverse Faber-Krahn inequality, tells that for this potential you can have it, but of course not for the standard one, because they are not gauge equivalent. So maybe this is how I see it.
Yeah. Well, I mean, I guess if the inequality is not given in terms of the standard physical potential, right? It is what it is, right?
Of course. But in fact, the conjecture of Elfer and Fournet is for simply connected domains. Right.
Right, of course. Do we have other questions for Luigi?
Can I ask you something?
Yes, of course.
So how attached are you in this proof to the fact that you're in a planar domain of R2? Can you do anything if you're in maybe open subsets of two-dimensional Riemannian manifolds?
We are attached in the equality, let's say here. Where this J of omega, this the derivative of the distribution function, okay? The point is that is greater or equal than 4 pi, and you have equality if and only if you have a disk, everything follows from the isoperimetric inequality plane. So you need to have, maybe you can do thing on the sphere. For example, we were thinking, but we then shift to other things on, you know, sphere or other spaces, but you need to have an isoperimetric inequality.
Right.
That's the point, yes.
Thank you, Martin, for the question. We have time for other ones if there's...
Maybe I have a quick one.
Go on, Marcello.
Thank you very much. Sorry, I mean, but how robust is this inequality with respect to, for example, the formation of the domain that is singular? So
no, sorry, can you repeat to the formation of the domain, which is
singular? So, for example, you have something that is, I don't know, it is no more smooth, but you have something that is say one, something like that at most, or even only continuous.
You mean cut stuff like that?
Yeah, exactly.
No, this I have to think a bit about, for I don't want to answer. So I have to think a bit about this question. I understand. Yes, it's we didn't think, because of course we confine to the smooth case. Of course, I have to just think.
Yeah, because you are using fact hypothesis of, for example, to be simply connected, but for example, the factoring really a smooth, let's say, domain. Maybe I miss where it used that. Okay, sorry, it was just a curiosity to know.
No, I have to think about. No, I was thinking about this. Of course, we. Of course, you see that the smoothness of the domain reflects in the smoothness of this omega, of this weight, G of omega. So we need. So already with smooth domains, we have troubles because G omega may not be smooth, but we manage. So maybe that's why I tell you that I have to think a bit about it. What kind of how this non-smoothness can reflect on this weight function. That's the point. So I have to think. Okay.
Thank you very much indeed. Thank you very much for your answer.
Is there any more questions for Luigi?
Can I maybe ask one more?
Yes, of course.
So in the beginning, you said that there was this inequality where if your domain fits inside of a strip of width epsilon, then you have that lambda 1 is less than epsilon square beta square over 4.
Yes, this is easy. And yes,
yeah, can you give a reference where that is seen, or?
This I think we wrote it in this first paper.
Okay, I'll have a look.
I think we wrote it. I don't remember. I don't. I think we wrote it. It's just you change gauge. You use a suitable gauge adapted to the strip. You use a test function, an easy test function for that. That's the proof essentially. But maybe we wrote it there. We wrote several examples. I don't remember if also this, but maybe yes.
Okay, thanks.
Anyone else has questions? Well, I mean, thank you, everybody, for this animated discussion, and let's thank Luigi again for this very nice talk. We will reconvene next week with a talk by Julien and moi on spectral statistics of negatively curved surface covers. So see you all next week.
Thank you very much, Jean. Thank you.
Thank you very much, Luigi. Have a great week.